I think one of the things that at least I feel is that frustration is such an important part of dealing with frustration, right? Because most of the time we are stuck in research. If we are making progress every day, then I would be if I was making progress, I would be skeptical if I'm doing the interesting project or I'm just doing something, some small extension of what someone has done. So how do we
I
deal with
see.
the fact that we are stuck for a long time?
The guest of today's podcast is Dr. Alok Laddha. He is a theoretical physicist at the Chennai Mathematical Institute who majorly works on soft theorems, S matrices, and the positive geometry program. So let's welcome Dr. Laddha on the podcast and listen to what he has to say. So, welcome to the podcast, Dr. Laddha. Nice to have you.
Thanks, Hassan. Thanks for inviting me.
So, before we talk about anything else, can you tell us a bit about the projects that you are working on nowadays?
Yeah, so as you said that, most of my focus has been on understanding, soft theorems, relation of soft theorems with asymptotic symmetries and, how, the ideas of soft theorem that we will discuss in more detail, how they sort of constrain the theory in the sense that what kind of symmetric groups are what is the symmetry of the underlying theory really, which is, naively we would say that, if you have some theory in flat space-time, then the symmetry is, global symmetry and Poincare invariance. But sometimes these so-called soft theorems, which are basically theorems about like low energy behavior of the theory, they sort of reveal interesting symmetry structure. So that's one class of projects that I've been working on. And the other is, as you said, about positive geometry program, where mostly the idea right now, my focus has been to understand, renormalization, of amplitudes and what insights positive geometry program provides for renormalization of scattering amplitude. So.
Okay. So, can you tell us a bit about what soft theorems are and why are they important?
Yeah, so soft theorems, I mean, so I guess the best way to explain soft theorems is that, usually when we do quantum field theory computations of amplitudes, we always use I mean, the sort of the strongest handle we have to compute amplitudes is via perturbation theory. So, we have some coupling in our theory and then we expand our amplitude in powers of this coupling, which, manifests itself in terms of Feynman diagrammatics, for example. But there is sort of a complementary perturbative expansion of the amplitude where the parameter in which you expand is not really parameter intrinsic to the system, but it's a parameter which is specified by the detector, which measures the cross section. So the idea is that, if you have some scattering happening and where suppose the scattering happens at some time t, so there's some high energy some scattering which happens at some time t, and the detector which is measuring the cross section, it gets switched on at a time much larger than t, for example. Then it turns out that these amplitudes, so you can use the fact that the time scale at which the detector has been turned on is much larger than the time scale at which the dominant scattering happened. And this, the inverse of the time at which scattering happened and the time scale at which detector was turned on can be used as a perturbation parameter. Now it turns out that this parameter manifests because in amplitudes we usually compute in momentum space, and this expansion I'm talking about manifests itself in the fact that if you have some QED scattering where you have electron and positron which scatter into bunch of charged particles and photons, then the detector which is switched on at very late time is only measuring soft low energy photon radiation. So the expansion that we spoke about manifests itself as the expansion in the frequency of the photon as compared to the energy scales intrinsic to the system that we are studying. And so this expansion, so as you can see that in this expansion, we are not referring to perturbative expansion in terms of the QED coupling or anything. And so it sort of reveals complementary insights into the behavior of the amplitudes. So the idea is that, if you compute let's say in QED, two charged particles, as we discussed, going into some particles and photons, and then if you do the expansion of the amplitude at any order in the coupling in terms of the frequency of the photon, then it reveals remarkable factorization properties, which are exact in the perturbative coupling, in the QED coupling. So they are, you take your amplitude, expand to all orders in loop expansion, and the soft, when you do soft expansion in terms of this frequency of the photon, they show some properties which are which are called soft theorems basically. And what they really compute is the amplitude for process where one photon or finite number of soft photons are emitted, divided by process where no such soft photons are emitted. So these ratios are what are called soft factors. And the soft factors are the power really lies in that are called theorems because naively we would think that there's some Taylor expansion, that we are just doing some Taylor expansion in the frequency of the photon. And if that's all it was, then it wouldn't be very interesting because I could take some amplitude at some order in perturbation theory and just do, where one of the outgoing state is a photon and I do expansion in the frequency of the photon. And that's not a theorem. I mean, that's just some expansion. The point is that it's a theorem because you don't have to do perturbative expansion at a given order in the coupling. So it's you're given some S matrix, and you say that this thing that we are measuring, the ratio of two amplitudes, where one photon is emitted with divided by a amplitude where no photons are emitted, and that amplitude is some exact to all orders in perturbative expansion the coupling. It's some factor which is why it's called a theorem.
Okay.
So yeah, so that roughly, I mean, that's I give an example of photons, but the same thing is true in gravity, and there are even in fact even in QCD some remarkable theorems like this are available. Um,
So you can have soft theorems for gluons as well.
exactly. So there is, in fact, it's more I mean, in QCD it's even more interesting in the sense that because in QCD you have what are called soft gluons, gluons whose energy is much less than the energy of the process, but you could also have what are called collinear gluons. And so the idea is that this soft theorem that we are talking about in QED gets sort of more refined, and what it goes under the name of soft collinear factorization theorems, which reveal interesting structure of QCD form factors, for example. So yeah, so
Right,
that's
right.
roughly, yeah.
Okay, so you said that these soft factors, which are like ratios of two processes,
Yeah.
they can be expanded in a Taylor expansion, right? So you will have a leading order term and then a subleading order term. So these different terms, do they give different information about the process?
Yeah, absolutely. So exactly. So the point is that if you, just as a specific example, let's just take QED, and then let's say that we have process in which in the outgoing set of particles there is one photon, which we call soft in the sense its energy is much less than the energy of the other particles which are involved in the scattering. Then, as you said, if you now look at the expansion, so we are not doing any perturbative expansion. So these amplitudes are, they are, to any order in the coupling. The leading term, which was derived by Weinberg, is a pole in the frequency of the photon, and it's called the Weinberg soft factor. And this is universal in the sense that for two reasons. One is that it's exact to all orders in the coupling, and it's also universal because if you add irrelevant operators to your Lagrangian of QED, then this factor will not change. So so it's so that's why, so that's the first factor. Now you can say, okay, what about this? Are there more universal factors than what Weinberg computed? And this was actually shown by Ashok Sen and Vishwajit Sahu in 2019 that if you look at the, if you do the, if you go to next order in your Taylor expansion of the soft photons, then there is a factor which goes as logarithm of the frequency of the photon. And this factor
Okay.
is also universal. It's exact to all loop expansion in the coupling of QED, and it is also universal under addition of irrelevant operators to the QED Lagrangian. And then
I
it
see.
turns out now that Vishwajit and Ashok, they took this further and further, and there are now a hierarchy of logarithmic soft theorems. So they are all some powers of logs of the frequency of the photon, and the distinguishing feature of these factors is that they are universal in the sense we are discussing. So when you do Taylor
I see.
expansion, you will also get terms which are not transcendental. There will be terms which are just some photon frequency to some positive power, for example. Those are not universal. But there
Mhm.
are these log terms which are universal, and it's interesting that they contain they all depend, they all depend on all these universal factors. They only depend on the momentum and the charges of the external particles and nothing else. So their functional
Mhm.
form is different, but they're completely fixed. Not They don't even depend on the spin of the external particle. So whether you have an electron or a scalar, these factors are the same. They only depend on momenta and the charges. And yeah, so that's but coming back to your question, that what new information they contain. and maybe we will discuss it, that the one way to understand the new information these factors contain is to look at the manifestation of these theorems in terms of the symmetries of the theory, and then you see that they are really, they are really word identities associated to some symmetries, and every such factor is associated to a different symmetry. In fact, infinite
I see.
dimensional symmetry group of the theory.
Hmm. So correct me if I'm wrong, but so since I don't work on soft theorems,
No,
but
yeah, yeah.
right, but one thing that I read quite some time ago is that in 2013 there was some work by Strominger and Cachazo, Freddy Cachazo.
Yes,
So what work
yes.
did they do in this
Yeah, that
paper?
was it's a beautiful piece of work. So what they showed in that paper was that this work. Let me go a little bit back. So this Weinberg-Soft theorem really came in 60s. So people knew in QED that
Hmm.
you had this universal soft theorem to leading order in soft expansion. And then Strominger, showed Strominger and his collaborators, students and collaborators showed that this Weinberg-Soft theorem really was a manifestation of an infinite dimensional symmetry of QED, which people did not really know explicitly before. Um, and so, motivated by this idea that soft theorems contain information about the symmetries of your theory, they looked at they did Taylor expansion of a tree level, what we would have called tree level S matrix in QED and gravity, and they showed that you had this what was called subleading a soft factor. So that was interesting in the sense that it's a Taylor expansion of in the frequency of the photon, but it's also a theorem which is only valid for tree level amplitudes. So, you may
Hmm.
wonder that, if you, if you are beyond, if you go beyond tree level, then what is the fate of these soft theorems? And
Hmm.
uh, this is where the Ashok and Vishwajit's analysis comes in, because as you know, in 4 dimensions, amplitudes are infrared divergence once we go beyond tree level.
Hmm.
And so it was never really clear, like what is the fate of these Kachazo-Strominger types of theorems once loop expansions are taken into account.
I see.
And
So so when you say that these theorems give us information about these infinite dimensional symmetries, are we talking about like asymptotic symmetries, or are they
yeah,
different?
because they are soft theorems, so they are theorems which are statements about the infrared properties of your S matrix.
Hmm.
So because of that, they sort of give information about symmetries which are in some sense symmetries which only act at large distance.
I see.
And that's why they are called asymptotic symmetries. They are really not global symmetries. They are symmetries that they are symmetries which look like they are only non-trivial at boundaries of your space-time in some sense.
See.
So
So for
yeah.
example, so correct me if I'm wrong. Um, so in for space time we have symmetries under boosts and translations and rotations, right?
Right.
Um,
Yeah.
so but we also have something called BSM symmetries. Are they asymptotic symmetries or are they different?
BMS, yeah, BMS in gravity.
Mm-hmm.
So that's this is a extremely interesting part of the story that in classical GR, I mean, completely independent of all these soft theorems and all this analysis, mathematical relativists from 60s knew that the asymptotic symmetries of no, if you take space-time which are asymptotically flat, and then you ask, okay, what are diffeomorphisms which are not what we would have called gauge transformations, in the sense that they don't go to identity, they don't act trivially on the boundary, but they still preserve the asymptotic flatness of the space-time. So these are
Mm-hmm.
they are diffeomorphisms, but they are called symmetries because they take a metric and they change it to a physically different solution of Einstein's equations. So although they are diffeomorphisms, naively we think
See.
diffeomorphisms don't change the physical content of the solution to Einstein's equation, but these diffeomorphisms do, because they are
Mm-hmm.
what we would call large diffeomorphisms. And it was known from 60s, in fact, that the symmetric group of space of solutions of Einstein's equation with no cosmological constant is not Poincare, but it's an infinite dimensional enhancement of Poincare group, which were called, which is known as you said, this BMS symmetric group. And
Symmetries. Right.
intuitively, the idea is that, our usual symmetries are Poincare, which are, translations and boosts and rotations. And BMS realized that you can have you have translations which are sort of angle dependent. I mean, they depend on the they are such that, if you look at a sky, if you think of, looking at a point in a sky, and you look at some at different points in the sky, like these translations act differently. I mean, they depend on the angle at which you are looking at these at the point in the sky. So they are parameterized by points in a sphere, in the on a celestial sphere, and that's why they are infinite dimensional. And it was always a
See.
mystery what these are good for. I mean, in the sense that if you study perturbative, which people also did from 60s, that study perturbative amplitudes in gravity, for example. Of course, it's not renormalizable, so you have to think of it as a computation of S matrix in effective theory. Then people you only have word identities for Poincaré, right? I mean, you didn't have anything else. So Weinberg had, for example, shown that if you look at the fact that gravity amplitude is gauge invariant under under diffeomorphism, I mean, under gauge transformations, that is what gives you equivalence principle, for example. So word identity associated to gauge transformations gave you told you that you have gravity has to satisfy equivalence principle. So for we knew what the word identity for global symmetries were doing for gravitational amplitudes perturbatively, but no one knew what this BMS thing was good for as far as quantum theory was concerned. So there was like two disconnected developments. One in GR, where people knew this rich symmetric group existed, which would map one solution of Einstein's equation with zero cosmological constant to a different solution, but it was not clear what these symmetries, how they constrain amplitude. And this where Strominger's work came in 2011, where he showed that, in fact, the Weinberg soft graviton theorem is really simply a consequence of this BMS word
Hmm.
identities. So that was
I see.
really where the, I would say, convergence of soft theorems and asymptotic, I mean, symmetries of S matrix, it sort of started.
Right. So it means that the soft theorem for graviton will give us information about the BMS symmetries, right? Would that be
So
correct?
yeah, exactly. So the Weinberg-Soft theorem is already is simply a statement that you have BMS symmetries, and its word identities are is the Weinberg-Soft graviton theorem. But now you have this new universal soft theorem. For example, what as I mentioned, that the next soft theorem which was found, which was as universal as Weinberg by Biswajit and Ashok, was this what is called log soft theorem. And
Hmm.
then the question is, okay, what are the word identities? What are the symmetries whose word entities are equivalent to this log-soft theorem? And then, it was, with my two friends, Andrea and Sangvin, we showed that there is enhancement of BMS, which are called super rotations, and its word identities give you precisely this, the second universal soft theorem, which is this log-soft theorem. So the expectation is that every universal soft theorem is revealing a structure of the of the symmetry algebra of your theory. And I think there is some conjecture and some evidence that the full symmetry algebra, where you package all these soft theorems together, it will be what is called a W infinity algebra, which is an infinite ladder of infinite dimensional algebra somehow. So if this turns out to be true, then these theories, like amplitudes, its matrices in theories like gravity, QD will be highly constrained. And it'll be interesting to
See.
look at the consequence of all these symmetries. Yeah.
So can you have soft theorems for scalars?
Yeah, you can have, but again, the point is that so I mean, you can certainly have. Say, if you have theory with massless scalars and you do Taylor expansion in the, so you have some theory where you have a massless scalar in as one of the final state particles or initial state particle, and you do a Taylor expansion in the frequency or the energy of the scalar. Then suppose you do a computation at what we call tree level, tree level. When you look at the soft expansion for tree level amplitudes, you see that once again, amplitude of for a process with the scalar divided by the amplitude without the scalar is some function of the moment of the other particles, and that's, you could call it a soft theorem. But there is no, as far as I know, there is no evidence that these are universal, in the sense that if I go to any order in perturbation theory, any order in loop expansion, and if I add irrelevant operators to whatever Lagrangian I started with, that these soft theorems remain same. And I would
Right.
insist that that's the real power of the soft theorems in QED and gravity. That the fact that they really give you a they are non-perturbative statements really for the amplitude. Yeah.
I
So
see.
you can
I mean,
have, but they could be just some Taylor expansion. It wouldn't. Yeah. Except there is, sorry, just I have to say one thing. There is, of course, one remarkable, I would say, in some sense, soft factorization for scalars, which are what are called Adler zeros. So if you have theories with spontaneously broken symmetries, and when you have these Goldstone bosons, and if you take their frequency to be soft, then the leading order term is not a pole in the frequency of the of this particle, but it just vanishes. The amplitude vanishes, and then this is a non-perturbative statement. So yes, I mean, so you can have interesting. That's one example I know, which is very powerful constraining, which is Adler zero, for example.
I
Yeah,
see. So as you said that if you want to have a sort theorem for a scalar, of course it has to be massless, right? I
yeah,
asked this question because so when you have like photons or gravitons, you can say that okay they are massless and it's a and they don't get mass because of loop corrections, but scalars can
right,
get mass through loop corrections, right? So
exactly.
but if they are massless, if the bare mass is zero, then they would be
Yeah,
massless, right? Even after loop corrections. So you
right.
can have okay, but what you're
Yeah,
saying
you
is
could
that they're
have,
not
but the point is
universal.
that even with that, it's not. I mean, so it's true that the mass could, the scalars could remain massless, but um, the theorem themselves, the fact that you get the soft factor, like the soft
Mhm.
factorization, whereas that expansion is independent of any order in
I see.
perturbation theory, and
Right.
in QED and gravity, I mean, because of the gauge invariance, this fact comes out, which is quite remarkable.
I see.
That
So
Yeah,
although we don't have, I mean, there are problems with particles with spin higher than 2, but can we like
yeah,
naively write down um, sort theorems for particles with spin 3, for example? Would it work or not?
yeah. That's an interesting question. But I mean, because we don't have a, so you're saying just write some higher spin Lagrangian
Hmm.
with a massless field and
Yeah.
yeah, yeah.
I'm
I mean,
asking this question because, for
yeah,
example, in holography, there are some scenarios where you have higher spin
yeah.
fields,
Vasiliev,
like
for example,
Vasily.
exactly.
Yeah. So
Yeah.
there, can you write down sort theorems for higher spin particles?
But that's I mean, in some sense, a remarkable observation you're making, because as you know, that these Vasiliev theories really are consistently defined only in ADS, for example.
Hmm. Yeah.
And interesting, I mean, if you think of, so let's say, some amplitude type computation in ADS, but ADS comes with a natural infrared scale, which is the length size of the ADS.
Right.
And so
Right. Right. Right.
even if you have some massless particles, you can never take their energies or frequency to be as small as you want, because they are always bounded from below by the size of the
True.
ADS, right? And
That's
so there
true.
are no real soft theorems in ADS, strictly speaking. I mean, in this sense, but of course, this statement can be more refined in the sense that um, I mean, this will be a little technical. So if
It's
that
okay.
you could write this as this, if you take some effective field theory in ADS, you could write the amplitudes in these theories in terms of Mellin diagram. What are called Mellin space. This Mellin space is like a very analog of momentum space in flat space, but because but it's not. I mean, ADS has no momentum space, strictly speaking, because it's curved. But in Mellin space, there is some sort of a soft type expansion that people like Fitzpatrick and Kaplan explored in almost 15 years ago, where they wrote down some kind of a soft photon type theorem. So it's not soft in the sense of the energy of photon going soft, but it is some other sort of soft limit, because the energy cannot, I mean, the wavelength of the photon is bounded by the size of the ADS. So we don't have the those type of soft theorems in ADS, but it is conceivable that you could have other um, so even for Vasiliev theory, coming back to Vasiliev, I mean, I don't know if anyone explored. It's a good question. I mean, I think that in principle, there could be something high. If you write some amplitudes in this theory in Mellin space, maybe
Hmm.
there are some
Yeah, I think
interesting factorization
the point
theorems. Yeah.
that you're making, I think that's a very good point. That you can't have like a totally zero energy particle there because there is a limit, right?
Exactly. Yeah.
So
Yeah. Yeah. Yeah.
right, right, right.
So
I
those
see. That makes sense
the
actually.
yeah, that soft expansion just doesn't exist in ADS. So
Hmm.
certainly, yeah. Although,
Okay,
I mean,
so
people do look at them. Sorry, just to, I mean, people do look at
mhm,
soft expansion in the following sense that they say that, okay, take the following scenario where you have two parameters in the theory. One is the frequency of your photon, and one is the size of the ADS. And now what you do is you take the size to infinity, so you take flat space limit, and the frequency of the photon to zero, such that the product remains fixed. And then you get interesting class of soft theorems which are not quite flat space soft theorems, because the product of the frequency and the size of the ADS is fixed, so you get some but it's it's not entirely clear
I
what
see.
what they mean, because they are not really flat space soft theorems, they are not really ADS soft theorems, they are some interesting statements maybe
Okay,
about quantum field theory. Yeah.
that makes sense. Okay, so let's come to the other, line of work that you do, which is a positive energy program. Sorry, a positive geometry program. So can you tell us a bit about what is this program?
Right. So um, let me put it in a context of ordinary quantum field theories. Not the origin of this program really came from looking at amplitudes in super Young-Mills, n equal to super Young-Mills, and that's really the where the program is actually most developed. But because my entire work has focused on looking at this idea of positive geometry in the context of non-supersymmetric amplitudes, like say ordinary garden variety scalar effective field theory. So I'll just say in that context. So the basic premise really is the following: that if you look at the the old S matrix program, which is the idea was that that there are some hard postulates that which are basically things like, let's say we are in flat space, so Poincare invariance, unitarity, crossing, and there was a postulate which was that in some sense the most profound but also the hardest to quantify, which was this analyticity postulate, that that S matrix is analytic away from wherever it has singularities. I mean, it sounds a little bit like a tautology, but it's the idea was that if you look at where the poles and the branch cuts are in your S matrix, away from wherever you sort of find them, S matrix should be analytic if you complexify all your momenta, etc. And the original program was that, can we classify all possible S matrices, which are simply functions, like complex functions of your external momenta, etc. Of course, scalars, because the S matrix will be Lorentz invariant, you have to look at just scalars constructed out of external momenta, polarization data, etc. And the idea was that what are all functions we can write down in the complex space of external data which satisfy these postulates, unitarity, analyticity, crossing, I mean, which are the three sort of main postulates. And that program, of course, because this analyticity postulate, so the program goal of the program is that you want some non-perturbative, understanding of the S matrix program. But the idea that S matrix should be analytic away from the poles and the singularity requires us to understand where the poles and the singularities are. And those we could only understand in perturbative theory. Like you take a Feynman diagram and you see where the Feynman diagram has some pole or some branch cut, etc. So it was not clear where all the singularities are of a local quantum field theory. And so the program, although it's a program which has given absolutely remarkable result in 60s, because all the results you obtained were all non-perturbative. The idea of defining S matrix as a fundamental object without using Lagrangian was sort of it was facing these roadblocks. I mean, so the positive geometry program in some different way, is asking this question, that if you just take space of all Lorentz invariant external data, which are just what we call Mandelstam variables, um, is there some, and you just forget Lagrangian or anything, like, and look at amplitudes, let's say, of garden variety scalar theories, let's say tree level amplitude or one loop amplitude, etc. What this can we understand these objects without invoking unitarity, analyticity, crossing? Like, is there some other fundamental principles which are giving rise to precisely these functions? So that's the goal of I mean, in some sense, that's the premise of the positive geometry program, that the amplitudes that we construct, at least perturbatively, let's say at tree level, one loop, etc., they are all really, you should think of them as volumes of certain geometries which are sitting inside the space of Mandelstam invariance. And these geometries, for various reasons we can go into, are called positive geometries. So the idea is that there are these geometries which are just living in this Mandelstam space. So it's not something that we are invoking physics to find. They are living there. We just have to go and look for them. And then if you compute their volumes, it turns out that they always seem to give you some function which has properties of amplitudes of a local quantum field theory. So I don't know if that, I mean, that's the
Right.
premise of the positive geometry program. Yeah.
So, what determines this subregion from the kinematical space?
Yeah, that's the remark. So that's where the, if you look at the way, I mean, of course, so by the way, this in the case of non-supersymmetric quantum field theory, this entire idea that that this such a thing could exist came from work of Nima and Song and Bai and Ye, and this. So they were the first one who realized that if you take what are called a class of scalar field theory with cubic interactions, they are called bi-adjoint. They are like you have to take scalars with colors, basically like gluons. Then the tree level amplitudes in these theories were really volumes of some geometries. So you can, as you are asking, where do these geometries come from? And the striking fact is these geometries actually have nothing to do with physics. So the idea is that mathematicians from 60s have understood that for reasons which had no connection with physics, for some combinatorial motivations, they always had some interesting objects that they had found, and these objects came, I can simply explain in 2 minutes as follows: that if you take a polygon is with n vertices, and let's say that you want to find all possible ways I can break this polygon into triangles. So if you take, for example, just if you take a four-gon, then then it means it has four vertices. There are only two ways to break it into two triangles. And the idea is that, so you take all possible decomposition of your polygon into triangles. Can you glue all these triangulations together into a single coherent object? And these coherent objects were found. It was called associahedron. It was found in 60s. Now, this is nothing to do with physics, some abstract, combinatorial object. So let's say it's some object like, let's say it's some specific uh, object of dimension, let's say D. So let's say in 3 dimension associahedron is some object, some complicated combinatorial object. Now, suppose you want to know how to draw it in Cartesian space. Now, of course, if I give you a three-dimensional object, there are infinitely many ways I can draw it in Cartesian space. I have to give you specification of where to put vertices, faces, etc. Now, one thing that mathematicians wanted to know was that combinatorial data that gave us the definition of this object, was that enough to also give you embedding of the object in Cartesian space? So if I take, for example, these triangulations and these chords, and indeed it was found that it's true that the same data that gives you the definition, abstract definition of the object, can be used to actually draw them. So that gives you one possible drawing. Of course, you could have many drawings. Now, what is remarkable is that if you identify this Cartesian space in which mathematicians are drawing these objects, and it is, this is what is called a canonical drawing, because it is coming, we are not putting extra input to draw them. It just comes from the whatever the ingredients was there to define the object is what gave you this particular drawing. If you now identify the Cartesian space, axis of this Cartesian space, let's say you have a three-dimensional Cartesian space, let's say some XYZ axis, and this you draw this three-dimensional object in that space. If you identify these three axes with Mandelstam invariants, then it turns out that this object is such that boundaries of these objects are precisely where poles of some tree level amplitudes are, with this cubic coupling. So, so this was the remarkable thing, that that mathematicians simply gave us these objects living in some Cartesian space, and if you identify this axis of Cartesian space with Mandelstam, then these objects had something directly to do with amplitudes of local quantum field theories. Um, and then it turns out that, so the fact that they are giving you amplitudes, let's say tree level amplitude of local quantum field theory, means that unitarity, things like unitarity and analyticity are emergent postulates. They are not some, because we are not building them in the program, right? Because we are simply discovering some objects mathematicians are giving us in Mandelstam space, and then we are computing their volume, for example, or canonical forms for these geometries, and they're giving us amplitudes of one or the other theory. So you see that, I mean, that's it's unlike the older S matrix program where the hard postulates were unitarity and analyticity. Here that postulates are emergent. They are not postulates now. They are like consequence of the fact that amplitudes are volumes of some geometries. And initially it seemed like this would only be true for tree level and only say theory with cubic coupling, what is called this phi cube theory. But then people realized that actually this was not true. I mean, there was this hierarchy of these positive geometries, and whenever you could draw them using this canonical drawing in the Cartesian space, and once you identify this Cartesian space with Mandelstam invariant, you start getting amplitudes of say phi-4 theory or phi cube plus phi-4 theory with different couplings and like that. And now it has now in last few years again, Nima and the collaborator Song and Carolina and other collaborators, they have actually taken this program to new heights where they have shown that if you go to any order in loop expansion, let's say for phi cube theory, again let's assume for simplicity that these scalars have colors, so they are like gluons in some sense. Then at any order in loop expansion, if you write the integrand for these amplitudes, unrenormalized integrands for this amplitude, they are always coming from these positive geometries. They are geometries which are coming from similar type of definition, in the sense that the example I gave you was that you take a polygon, you triangulate it. If you take a polygon, but you remove a hole from it and then you triangulate it, then you get some geometry which gives you one loop unrenormalized amplitude, for example. And if you take I'm giving you a very schematic picture, but so it's like a and it's like you don't I mean the physics part comes only when you identify where you are drawing with physical variables. Up to that point, it's really something which comes from some math. And so it's so that's the
So,
program.
one thing. So, one of the postulates, I think, I don't know if you mentioned it, but one of the other postulates is locality as well. That also emerges, right?
Yeah, so exactly. So locality and analyticity are deeply intertwined.
Hmm.
And so exactly, yeah.
Okay.
So
So,
yeah,
one thing that I'm trying to understand is this. So, you can write down field theories which are not unitary. For example, there are examples of
right.
non-unitary CFTs. For example, the Yang-Lee H singularity, right? So,
Yeah,
if you have a field theory which is not unitary, you can write
yeah,
down processes in that theory which are not unitary as well. So, what I'm trying to understand is this: if you have an amplitude which is not unitary, can you
yeah,
convert that into a volume of something?
yeah. That's an excellent question. And I mean, well, if these positive geometries are really what we call convex geometries, in the sense that if you draw them, their shape are convex. And um, it's an interesting question. So I think that if you um, so far what we know is that if you take these geometries which are this which have the specific convexity properties, etc., and we draw them, um, and we look at their volume, then they are always able to reproduce for us unitary amplitudes. And the reason they're able to produce unitary amplitudes is very simple, that just to give an example in tree level, for example, that these geometries have boundaries. So they are like some convex objects with boundaries, but the boundaries of these geometries are also positive geometries. So it's a by I mean basic in a simple way to understand positive geometry is something. It's an object which has boundaries of all lower dimensions. So if you take a d-dimensional positive geometry, it has boundary of dimension d minus 1, d minus 2, all the way to points basically. And so
Mhm.
so when you for example compute when you go to the boundary of this positive geometry, when you draw them in Mandelstam space and go to the boundary of the positive geometry, and now you look at their volume or their forms, whatever, they give us amplitude where you have basically gone on shell on one of the channels. And so
Mhm.
and that's really what unitarity is at tree level, right? That if you go to if you go on shell on any one of the channel, then amplitude factorizes into two on shell lower point amplitudes. So
Right.
the fact that these geometries are have boundaries of all codimension, which are also positive geometries, gives all unitary amplitude. So it could be that there are other class of geometries where if you go to some lower dimensional boundary, it's no longer a positive geometry, and that could give
Mhm.
us a non-unitary
I
amplitude
see.
also. But the right now the thing is that the program, the idea of the program is that um, I mean, at least the way I appreciate this program is that, really it's more like a bootstrapping, in the sense that let's not assume what theories we get. Let's look at these objects, let's look at their geometries, and let's see once you write down functions, volumes, for example, let's see whether the volumes are amplitudes of some local unitary quantum field theory or not. And so far, we find that they always turn out to be, which is quite remarkable. Um, uh,
Right.
if you give me some particular Lagrangian and say, can you find a Paul geometry? I think it's generically it's always going to be very hard. So
Mhm.
the idea is more the other way. That you
Other way around.
take
Okay.
these
I
naturally
mean,
defined math objects and see whether, yeah.
right.
Yeah.
So what I'm trying to understand is that in this context, what does unitarity mean? I mean, does unitarity
Yeah.
or in other words, what is unitarity a consequence of? So is it a
Yeah,
consequence
it's
of
a
the fact that
consequence of the
the
fact that the
boundary?
boundaries are also positive geometries.
I see. I see. So
Yeah.
if the boundary, if you have at least one boundary that is not a positive geometry,
Yeah,
then
yeah,
you will
then
break
definitely unitarity
unitarity.
will be violated. Yeah, yeah.
I see. So can you do this thing that you so these geometries, they have a single boundary, or can they have multiple boundaries?
No, it's a one. Each geometry is like one convex object. So it has one connected,
Okay,
always
I
have
see.
one connected boundaries.
One
Yeah,
connected boundary. I see. So it means that you can't say that, oh, this theory or this process is more unitary than the other one. It's either unitary or not. Correct?
exactly. Yeah,
I
exactly.
see.
Yeah,
So okay, so that's for unitarity. What about locality? How does that emerge?
yeah, yeah. So I mean the way locality emerges is the fact that um so as I'm saying that once you canonically draw them in this Cartesian space, then you can put like volume measures on these geometries, or what we would technically call some differential forms. So if you now this differential form, because these geometries are such that because they you can ask the following question, that are there some differential forms that you can write on these geometries once you draw them, which have poles on all the boundaries of all dimensions, but only on the boundaries, nowhere else. And this is some algebraic geometry statement. Again, this absolutely remarkable result was proved by Nima, U. Thomas, and Bai in, I think, 2017, end of 2017, that with each positive geometry, you can associate a unique form of. So if the positive geometry is dimension D, then there is a unique form of dimension D which satisfy these properties, that it's smooth everywhere except on the boundaries of the positive geometry. And now, so this form is such that if you they only have poles on the boundaries, and this really is a statement of locality. The fact that if you take a tree level amplitude, then it only has simple poles, and the fact that these forms for these geometries, only have simple poles, they naturally tell you that, for example, like I'm right now saying a tree level, the amplitude will always be local because you don't have any complicated poles, or, some crazy thing like that. You always have simple poles. And the same statement goes through for at loop level, at the level of integrand. So all the integrands have simple poles because they are all come from these canonical forms, etc. And that is what you require for a local quantum field theory, right? Because if I write a Feynman diagram expansion and I write a loop integrand, then you will always have simple poles. Like you will have propagators, but each propagator will give you some pole, right? So that's how locality manifests itself. Um,
I see. I see. Okay, so if I ask this question that if you write down, if you try to, I'm pretty sure that if I ask you this question that how many positive geometries are there, I think the answer would be infinite, right?
yeah, yeah, yeah.
Okay, so it means that so can we ask this question that are there do you have more positive geometries, or do you have more geometries which are not positive geometries? Is that a sensible question to ask?
Oh, yeah,
Or
yeah, yeah, definitely. I think there are positive geometries are very constrained. They are very not, even though they're infinite, as you are saying, they are
Mhm.
very generic. I mean, because they have to
Okay,
satisfy several properties for it to qualify as a positive geometry. So,
I see. So
yeah.
does
I
this
mean,
mean
just to
that?
give an example of a geometry which is not positive, like a disk. So, if you take a disk, then
Mhm.
it's a two-dimensional object which has it has one boundary of dimension one, but it has no boundary of dimension zero. Whereas if you take a
Oh, okay, I
triangle,
see.
that's a positive geometry.
Mhm.
So you can now imagine, I can always smoothen out my positive geometry to
Right.
get non-positive geometries by,
So, so,
removing boundaries of some dimension, lower dimension.
so would it be correct to say that positive geometries are like symmetrical complexes?
Um, Well, simplicial complex certainly positive geometries, but uh, uh, well, actually, strictly speaking, simplicial complexes are what we call dual of positive geometries, but that's a little
Mhm.
technical. But you can have positive geometry which are not just simplicial complexes, very nonlinear
Okay.
geometries. I mean, as long as they have these boundaries of all dimension, they would qualify, roughly speaking, as a positive geometry. I mean, there are some subtleties, but let's say for purpose of this discussion, but you can have
Hmm.
curvy. For example, a very interesting example of a positive geometry is if you take the moduli space of for the string amplitude. Let's say for the tree
Hmm.
level string amplitude, just take the moduli space, which is n punctured moduli space of n punctured Riemann sphere. This space is not compact. Um, but if you take if you take like a real section of this space which corresponds to open string amplitude, so which is basically moduli space of n points on the boundary of a disk.
Hmm.
This is a real moduli space. So instead of points on a sphere, you look at a disk and look at points on the boundary of a disk, and all configurations which are related to each other by SL2R, you identify them. So you get some moduli space for tree level open string amplitude. If you compactify this space, you get a positive geometry. But this geometry is
Okay.
not linear. I mean, it's some complicated, geometry.
I see. I see. That makes sense. So, actually, my when I asked the question that do you have more positive geometries than geometries which are not positive, I wanted to ask that since you said that positive geometries are very constrained, right? So
Yeah,
it would it be correct to say that it does give you the conclusion, which is not unexpected, that the number of unitary amplitudes is much smaller, right?
exactly,
I
exactly,
see.
exactly. Yeah, that's a great way to put it. I
Okay.
completely agree. Yeah. So that
Right, right. That's actually quite reassuring.
yeah.
So, do you have examples? I don't know if you probably you did mention it, but do you have any examples of geometries um, which correspond to processes which are not unitary? Or do you have some constructions which are corresponding to processes which are not unitary?
Um, Yeah, that's a very good question. So I don't know if explicitly someone has looked at it. There are these geometries I'm not terribly familiar with, which were investigated recently by Nima, Yaroslav, Johannes Henn, etc. They are called negative geometries, but they investigated them in the context of computing form factors for in I think in the Coulomb branch of n equal to 4 super Young Mills, etc. But I don't know if um, geometry, let's say for tree level amplitudes, which gives you I mean, I think we could construct one, as I'm saying, you could take a positive geometry and smoothen it out so that, let's say vertices are removed, and presumably they would give us amplitudes which are not unitary in all channels. But
I see.
I haven't seen any example like, but I suspect it shouldn't be that hard to construct some artificial example like
Okay.
this.
So,
Yeah,
I mean, the answer to this next question may be a bit technical, but you can try to make it, as devoid of jargon as
yeah.
you can. So some time ago, I was, watching a talk on, positive geometry program, and they used this object called gentle quivers. So what are these objects, and why are they used in this program?
Yeah, that's an excellent question. So the idea is that I was mentioning before that. So this is where the math thing really, in some sense, came in. That if you start, let's say, so the example I was giving you, let's say you start with some completely, let's divorce from physics, some completely abstract polygon. Let's say a polygon with four vertices, and there are two ways to triangulate as this object, and combinatorially, then what we get is a this gives us what is called one-dimensional associahedron, purely combinatorially, and this is an object which has two vertices, which are two ways to triangulate, and they are connected by a line which is no triangulation. So that's this object combinatorially. And now, as I was telling you, that one of the things that mathematicians were interested in is, so it's like a line with two vertices. Now, if I ask you, can you draw this in a Cartesian two-dimensional space? I mean, there are infinite ways to draw it, but you will have to give the slope and you will have to give the location of one of the endpoints, right? So, like there are so if you just want to draw it, you have to give this data. This data doesn't come from the geometry itself. The data is something we are providing externally. And the mathematicians, what they realized was that given this structure of triangulation, you can associate a particular graph to it, which is called this quiver. these graphs are such that they have they have they are really, if you, I mean, they are really defined in such a way that they have vertices either on the external edge of the polygon you started with, or on the chords which dissect the polygon into triangle. And these are called gentle quivers because they have two type of vertices: one which sit on the chords which are inside the polygon, one which sit on the external edges of the polygon. And it was some representation theory of this quiver which gave us this, what I was telling you, canonical drawing, which turned out to be relevant for physics, which was remarkable. So,
Okay, I see.
the trajectories goes from some combinatorial geometries to some representation theory via some graphs and quivers um, to physics, to physics.
Mm-hmm. I see. So can you use I don't know if this question makes sense, but let me know if it does. So can you use this program to study scattering processes in holography?
That's an excellent question. I think that, yeah, I think this is a really good question because, one of the things that I found always amusing is that, if you look at what we were discussing, this older analytic S matrix program, and if someone, if someone asks us, okay, can you give one example where this program is explicitly realized of this idea that I want to classify all S matrices from some postulates? Now, we have an answer to that from ADS CFT that all S matrices in ADS are coming from postulates of conformal field theory on the boundary. So,
Mm-hmm.
in that sense, ADS CFT gives us an explicit realization of the analytic S matrix program. This point was made by Sasha Zhibodov in, I think somewhere, which I found very revealing. And so yeah, I find it like, I mean, this is a very incredible thing that given I think we know that if you give me some tree level amplitude with say this colored phi cube theory, we could write it in terms of these positive geometries. They are combinatorially the same positive geometry as associator, but they will have to be drawn differently for us them to give us ADS amplitude as opposed to flat space amplitude. Because we will not draw them now in Mandelstam space because there is no Mandelstam space in the ADS, right? We would have to draw them somewhere else. And if you do that, then of course there is some connection of the geometry with CFT. I mean, so but my feeling is because we understand conformal physics a lot more, making this connection would help us understand positive geometry program a lot more by taking CFT. So it will be, usually these things are two-way streets also, right? I mean, this positive geometry program from math perspective is also developed much more in last few years because physics has informed it. So,
Mm-hmm.
in fact, this quiver, gentle quiver realization, this canonical drawing I was telling you about for association, actually it was found by Nima Song, what is called ABHY, association, by physics ideas. So they didn't use any quiver or anything. Then later mathematicians came and said, look, this is actually a canonical way to draw it using some quiver analysis. So usually these things are informing each other. So it is possible that, when we connect it with, if we connect amplitude in ADS with positive geometry, which I strongly feel should be definitely be possible, and then it would have an interesting interface with conformal field theory on the boundary.
Right. I
Because I
see.
think that's where we know the analytic arithmetic program so excellently well because we know we understand unitary CFTs. So yeah, I mean this another I mean, yeah, it's a very good point actually. I'm not sure if anything done in this regard. I hope I'm not missing some reference,
Mhm.
but I'm not seen anything.
Okay.
Yeah.
So you did mention, the possibility that you can use, this positive geometry program to study closed string amplitudes and open string amplitudes. But can you use this program in string field theory, or are there some hurdles if you want to use it there?
I don't think anyone has looked at this so far. I mean, of course, one of the things that the Princeton group has done recently is to really use the insights of positive geometry to write, for example, open string amplitude, not string field theory, open string amplitudes in terms of parameterization of moduli spaces, which are for some purposes far more convenient than let's say Schottky parameterization or just the worldsheet coordinates. Um, um, it's interesting. I mean, I don't think string field theory. Um, uh, I think it should be possible because string field theory, as far as I understand, I mean, string field theory is above my pay grade to be honest. But what I understand from talking to Ashok and some of my colleagues here who work on it in Chennai is that you write amplitude in terms of diagrams again, Feynman diagrams.
Mhm. Yeah.
And the idea of polygeometry is to never look at amplitude as sum of diagrams. Amplitude is something fundamental. It's like a volume.
Hmm.
When we split it into diagram, that is just one representation of the amplitude. So in
Right.
positive geometry program, diagram comes, take a secondary place compared to the S matrix, whereas in perturbation theory from Lagrangian, it's the other way around. So yeah, it's an interesting point. If you take up, let's say, some 4-point amplitude in string field theory, full amplitude, not just one diagram, can it be obtained from some volume of some positive geometry? I guess what I understand is that these amplitudes are very complicated in string field theory, even like 4-point amplitude. So maybe that's
Oh,
why
yeah,
people
yeah.
have
I think the
but
number of
it's
people
an
who,
excellent, excellent point. I mean, I think
right.
this,
I mean, I'm
yeah,
not surprised that no one has looked at this because the number of people who work on string field theory is small anyway. So
yeah,
you need a lot of people to work on string field theory to look
yeah,
at this
yeah,
point. So okay,
yeah. I mean
see.
that there is a colleague of mine, Roji, who is a strange thing field theorist, and he's begun exploring these ideas now seriously. So I hope
Okay,
we will see some nice results from him.
sure, that's great. Okay,
Yeah.
okay. So I have some questions, and then I have some questions from the people before we wrap
Okay.
this up. So, when I talked to Suvrat Raju,
Yes.
he mentioned your name, and he said that you have this ability where you know literature more than most people that he know. So, do you have any tips on how to know literature
Oh
very
wow.
well?
I
Yeah.
think Surat was just, we are good friends, so you may be being too kind. I mean, no, I mean, I don't think no, I don't think this is true. I mean, I think, of course, we all read so many papers because beyond what we work on, we are interested in, different
Mhm.
ideas and development. So in that
Right.
sense, of course, um, no, I mean, I think maybe I could say one thing. I mean, it's not like, but again, I don't think I have more knowledge than others. I think Surat was just being too gracious. But I mean, one thing was that I worked, in my PhD and postdoc on loop quantum gravity only. And but I was always interested in string theory and especially analytic S matrix program, although I was never having concrete questions, or whatever questions I had, I was not able to make progress. So but at some point, that thing that we read more than what we work on helped me to at some point I could make some questions which I could then answer, what I'm saying. So in that sense
Mhm.
it helped me. But yeah,
So are there any ways that you are there any ways that you use to keep yourself informed of the literature, or you just do
um,
normal things, or is there something
yeah,
non-trivial
not
that you do?
normal thing, but yeah, I mean, in the sense that there were some things that I was, which were away from what I was working on, like loop quantum gravity, which I was very deeply interested in. I think one is this S matrix program. It's something that I studied older program as a student. Of course, I would forget most of the things because I was not, working on any projects. But so any papers that came out, I remember when color kinematics duality came out in 2008 when I was finishing my PhD. I was extremely excited, and I spent so many weeks trying to understand, that
Mm-hmm.
paper. So yeah, I
I
mean,
see. So one
yeah.
question is regarding something that you just said. How did you convert from working on loop quantum gravity to working on string theory? How was that journey? Was it hard or no?
No, well, I mean, it was actually, the what I mean. Um, Yeah, so I mean, it was I mean, I mean, it really, in some sense, it was a natural physics. It just happened through physics in the following sense that, so I was working on, what is called old canonical loop quantum gravity. I mean, there are now two versions. We don't want to get into it. It's like some
Sure.
different discussion. But what, at least in my opinion, whatever I thought were the interesting questions, I was not able to um, answer them. I mean, in the sense that, I was working, most of my work was about, making Wheeler-DeWitt equation regress in a loop quantum gravity, like the Hamiltonian
Hmm.
constant regress. And I was working on various toy models, but it always seemed like whatever I put in, I mean, the efficiency of my results were not good. Like whatever I put in, I had to put so much construction to make things work. You know what I'm saying?
Yeah,
Um,
right.
and from 2011 and 12, I was looking at BMS, with, I was discussing some project with some students. I mean, when I was a postdoc, which was all classical GR BMS. So at some point when the soft theorem BMS analysis came in, with a close collaborator and friend of mine, Miguel, we immediately had, we realized that there was some connection with some parts of classical BMS, old BMS, that then we tried to explore. So it naturally happened that I there was one class of questions where I was able to I was more excited about at some point. And I don't want to say in LQG it was, I would say that, at least I was not able to make progress in the question I wanted to
Mm-hmm.
ask. And so, there was a period where I was working on both, but then um, it just fizzled out because, any other things I was more excited, more and more excited about, the soft theorems and BMS. And
I see.
it seemed like, things were working more naturally. It was not like I had to, in pure quantum gravity, unlike in string theory, and it is not just about loop quantum gravity, also about other approaches to quantum gravity, because you start with almost very little. You don't make contact with effective field theories or quantum field theories. You have to construct the theory. It is not that you're discovering theories.
Mm-hmm.
As we are discussing about positive geometry, it's not we are not constructing. They are just sitting there. We just find them, find the volume, and it
Yeah.
turns out they turned out that I think just at a deeper level that is often missing in any pure quantum gravity approach, because you start with something exotic and build things.
Yeah.
So it's more of a constructive. So I guess it depends on the taste also. That I
Right. Right.
think
Right.
I generally discovery is more exciting for many of us than inventing. No, that's
Right.
you know
Right.
what
Right.
I'm saying. Yeah.
Right. 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 Yeah. Okay. So, one more question that I want to ask you is that, I mean, so since you had this, journey where you had to, juggle,
Yeah, yeah.
change the problem that you're working on. So, do you have any advice for younger students about how to choose what problem to work on?
No, I mean, I shouldn't say I shouldn't give. I mean, I'm not a very, I'm not a very successful in that sense physicist to give a advice. But I mean, so take it with a big grain of salt, because it's not like
Mm-hmm.
I've been successful at that level. But I would say that it's always good to keep a long-term goal mind, in the sense that, always good to keep some bigger question in mind, even though we may not be able to solve it. We solve some small problems, but with the context, that there is some bigger picture in which we are trying to place our problem. And I think it does two things. One is that you work long term on some ideas, step by step. And
Mm-hmm.
also, I feel that you gain deeper understanding in the subject if you work on it for a few years like this,
True.
so that's all I would say, that, I mean, in the sense of, rather than shifting to, because there are so many exciting ideas and papers that come, I mean, it could happen. Sometimes I feel that, hey, this is something nice that came in holography. Maybe I could think about it. But then, I mean, the deeper perspective I would may not have. I mean, there may be some technical thing I would be excited about, but I mean, there is no long-term question necessarily that I have in mind when I am excited by the technical thing. So
Right.
I
Right.
would
Right.
generally say that one is to balance.
Okay.
Yeah.
Okay, so I have some questions from the people. So let me go through those
Okay.
questions. So one question is that, okay, so this is a generic question. Some of these questions may be open-ended, but we can try to make
Yeah.
them
Yeah. No. No
precise. Okay.
problem. Yeah. Yeah.
Okay. So the first question is that, what are the most interesting, in your opinion, what are the most interesting and important problems to work on over the next decade?
No, I think that this is really, something that I think people should definitely work on, whichever, direction that, I mean, there are so many exciting, I personally feel, direction, from all the way from, as we are saying, string field theory to, at least personally, I feel the swampland program, which it's something that I try to study a little bit and find extremely promising, but I never work on it, to, developments in amplitudes, non-perturbative aspects of QFT. I think I would say important. I mean, so I can only comment on the important questions in the subject I am,
Yeah, I mean, it's about your
working on.
opinion.
And
So,
yeah, yeah. So in positive geometry, I would say, for example, to really push the program further. I mean, in the sense we are already seeing that, some synthesis of these ideas, that if we take one class of positive geometry like associahedron, it is enough to generate for us a wide class of scalar amplitudes. There is a way to spin up this associahedra to get, gluon amplitudes. And so it seems like there is some really universal thing sitting inside these positive geometries, which are not even theory specific. So, I would say the bigger thing would be to really, push this to at the level of some analytic mathematics program, that we can clearly say that, look, these are the postulates, they give us unitary local quantum field theory amplitudes. That's one bigger thing. And yeah, I don't know, the other important, um, I would say that, I mean, I would say that observables in, asymptotically flat S matrix in gravity, for example, I find that to be a very promising direction because of the fact that, of course, the theory is non-renormalizable, so we have those problems, but also the theory has infrared issues. And, to find infrared safe observables, even though the S matrix itself is not well defined in the infrared because of the infrared divergence, I mean, that's classification of all these observables, which are infrared safe in quantum gravity is another thing that I think, because it could lead to holography in flat space, could lead to some ideas about holography in flat space.
Okay.
Um,
So the next question is that, do you have any advice for late year PhDs or early stage postdocs?
I think you are in a better position to give this advice. I mean,
No, I mean you're senior than me. How am I? How
yeah,
am
no,
I
no, in the
better?
sense that you are experiencing the thing right now. I
Oh
mean,
yes. Okay.
yeah. No, I mean, I think this is difficult to say because it so much depends on not only the student but on the advisor and the environment. I mean, I think 99 things can go wrong in PhD and only one so it's a very hard, challenging thing to do PhD, I personally feel, because it all comes down to many factors have to go right, not just your hard work and your motivation, but other things also have to go right. But I would just say that people should no, I mean, again, don't you shouldn't take my advice too seriously, but I would say that if you have a concrete program, whatever it is, and you have some context of your question, I think you'll naturally be excited, and then I would say that's one thing one should keep in mind. But this again turns out to how much freedom you have to implement your ideas, to look at your ideas. And as with the postdoc situation in different countries, in our field being in such a crisis now, including in India, I think yeah, I don't know, maybe I wish the question was a little more specific. This seems very general. I mean, I'm not sure if
It's
I'm
a
doing
very
justice,
open-ended
but
question.
yeah.
Okay.
Yeah, I don't. Yeah, yeah, yeah. I don't know. Maybe I mean, if I asked you this question as a, not advice for postdocs. Of course, you are not a postdoc. But what advice would you give to students little younger than you, for example?
I mean,
PhD.
I would say that if you have made any mistakes in the past, don't beat yourself up every day on your
Yeah,
for
that's a
those
great point.
mistakes.
Yeah, 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 yeah. I think you're right. Sorry, I should have said this. I think one of the things that at least I feel is that frustration is such an important part of dealing with
Mhm.
frustration, right? Because most of the time we are stuck in research. If we are making progress every day, then I would be sick. If I was making progress, I would be skeptical if I'm doing the interesting project or I'm just doing something, some small extension of what someone has done. So, how do we
I
deal with
see.
the fact that we are stuck for a long time? Is yeah.
Okay, so the next question is that theoretical physics has become very technical for people who are not affiliated with any university to make any significant contributions to physics. Do you agree with this statement?
Um, Well, I mean, there are, I guess, two ways to look at it, right? One is statistically. I guess it's definitely harder for people outside academia to in physics. But there was this example in maths. Sorry, I may be saying his name wrong. Professor Zhang, I think, who did this prime factorization, who was
Yeah, I think
uh,
his name is Yitang Yang. Yeah,
right. So, which was remarkable. I think he was in. I mean, he was of course PhD. So, but I think he was in a school
I
or
think he was
college.
in Michigan. No, wait,
Right, right, but
yeah,
not in a main
probably.
what one call mainstream academia at that point. And he
Yeah.
worked on this very hard problem. So I wouldn't say it's impossible. I mean, honestly, I do know some people in India who I mean, so first of all, they have done PhD from good places, etc. So in high energy theory, but because of various circumstances, they left physics for a while, and now they on the side they do work on. They actually publish also, like they work on mainstream, not out there ideas, something that they were doing, and often on with collaborators in academia, they still publish some papers. So think it's possible.
Okay.
But statistically, I mean, I think everything is possible, right? I mean, so we can't say that it's impossible, but I think one should also be careful because, I mean, I think what academia gives more than anything is that, it gives a constructive criticism environment also. Like, there should be people to tell you why your ideas are wrong also. So,
Hmm.
working in isolation, that is one risk one would always run into, right? We wouldn't, even if we
True.
are critical, we would not always, we would need someone else to find holes in our arguments, which we may not have if we are outside academia. So I don't know.
Hmm.
That's one major risk I would think. But otherwise, yeah.
Okay.
Um,
So the next question is that I have a, I mean, I don't know why it says weird, but it says I have a weird query. I have had my master's in maths from a top Indian institute, but due to my lack of awareness, I didn't do my PhD. So how do you reckon someone like me with a gap of almost 7 to 8 years can now go back to it?
Yeah, I mean, I guess, I mean, the person depends on his or her circumstances. I think idea would be to try to go to PhD if they want to pursue it. I must say that in India there is, I have seen in many places cultural barrier to taking older student, which is really unfortunate. But I understand that in US it may not necessarily be so. In the sense, I know people who older people who do PhDs also, right?
Yeah.
But I know that in India, not everywhere, but there are many places where this is, oh, if you take someone who is in their late 30s or something, what will they do afterwards? And, this kind
Yeah.
of, so
Are there
there is
age
that
limits?
barrier.
Are there
Sorry?
age limits in India
No,
for
no, there's no
PhD
official
students?
age limit at all. But I can honestly say that this is which I deeply disagree with. Honestly, it's like people's decision,
Hmm.
right? If they're good, they want to do, they should be able to do. But
Yeah.
not everyone shares this view, and this barrier certainly I have seen as of in academia. So that challenge is there in India, but I think if you can cross that, I mean, you should just do it. I mean,
Okay.
yeah.
So the next question is that do you think that, sorry, what do you think about the future of theoretical high energy physics people because the job prospects are very bad?
Yeah, I
It's a
mean,
very hard question. I understand.
yeah, it's a very hard question because it is true, and we see in India also a situation is right now very bad for a variety of reasons, also including, as there is a lot of backlash against high energy theory, and even in physics departments, and the number of jobs are less also, and but um, yeah, I mean, at this point things are a bit bleak, at least in India, I must say. So my advice would be, if you want to do, but if you still want to do PhD, I think you should do it, because you just be aware that 5 years you can have good fun, and after that you may have to go for other jobs. I mean, in the sense of in case you don't get to continue academia. But one good thing, I guess, is that the skill set you require now with the in many different sectors, like especially in AI and all. I mean, they do look for people with analytic skills, like people who do theoretical physics or mathematics. So um, I think psychologically, if you are ready, that look, I can have a very productive time, and but maybe even if I do very well, um, things may not work out. I mean, it's very depressing, but it's how it, this is the situation right now. That, but we don't know, right? I mean, if it's a phase or, I mean, I would say the subject itself is very exciting. I mean, that's the irony of it also, right? In spite of the in spite of the fact that we have, of course, in some level, a crisis in the sense of the fact that standard model works too well, and we need to really look at LHC data much more closely, and to see whether you find real signatures of behind standard model physics. But at the other side, we also have cosmology, which is seeing this remarkable, so many different paradoxes are opening up, and so much more data is coming. So, and theoretical development is, so I mean, I think the subject has this dichotomy right now, right? That it's there are a lot of exciting ideas in theoretical high energy physics, but the job market situation doesn't seem to reflect the fact that the subject is not dead at all, right? Far from it. I mean, it's I mean, that's yeah. I
Okay.
don't know if that answers the
Okay.
question.
So
I
the
don't know
next
if,
question,
yeah.
I mean, I don't think that there is a way to really answer this question because
Yeah,
we
yeah.
can't
It's
change
also
what's
no
happening,
beyond, it's
of
beyond
course.
our control, to be honest. So many factors go into all this. So
Right.
yeah.
Okay. So the next question is that, well, I don't know if this is relevant for you, but okay. So it says that, do you have any thoughts on gravitational wave memories and spin memories?
Yeah, yeah, because gravitational wave memory is really just one way to write the wine box of factors. So, the gravitational wave memory is directly tied to, and including the spin memory, for example. These are directly tied to asymptotic symmetries and soft theorems. I mean, they are really some manifestation of these. I mean, so if you take asymptotic symmetry like super translation and look at the chart, like take gravitational scattering and see what is conserved, That conserved charge is really what is this gravitational memory. And spin memory is more subtle. I mean, I think we have to go into more detailed discussion. Maybe I'll briefly summarize. So on one side, if you look at it from the amplitude perspective, the spin memory is associated to that, the soft expansion of amplitude in the soft frequency of the graviton, which occurs at the order frequency to the power or energy to the power zero. So it's like if you do a LoRa expansion, then it's a term which is not logarithmic in the frequency of the photon. It's a regular term. These terms are not stable under loop corrections. They get totally ambiguous under loop corrections. So as I was telling you, that the universal terms are really these log terms, which are independent of the theory and independent of what order you go in the loop expansion. So from that perspective, spin memory looks like something which should be valid only for tree level. But on the other side, this spin memory observable that people talk about in classical gear is for bound orbits. They are for inspirals, for example. And I mean, it could be that for inspiral, these are really non-perturbative observables, whereas for hyperbolic scattering, I mean, for bound orbits, I'm saying, for hyperbolic scattering, they are not. And this is an interesting open question, in my opinion, to really explore the robustness of spin memory.
Okay.
Yeah.
So the next question is that why did you leave? I mean, I think you have kind of
Yeah.
answered this question already, but if you want to add something, you can add. So it says that why did you leave loop quantum gravity? Did you no longer find it promising?
Well, I mean, yeah, I definitely, yeah, I mean, I shouldn't say, because I haven't kept up with the subject at all, honestly, in last 7, 8 years. So I really don't know much about what has happened in that time. But because many of my friends who are also working also no longer really work in a loop. They've all, gone into gravity or some high energy theory related areas. So including my close collaborator Miguel. So I mean, I'm not that aware what has happened now, but I must say from my perspective, as I told you, I did find I mean, it was a slow process, not something that you wake up one day, but I realized that this idea that we construct a theory rather than discover was not something that I found that as a process. I mean, regardless of success or failure of LQG, I just found the thing not that exciting for me. That we have to put inputs to make something work. We are not I mean, yeah, I mean, I already said that. So that um, and another thing, as I said, is that the problems I thought were interesting, which were about gravitational observables and about whether we can really define Wheeler-DeWitt equation, which retains covariance of the theory, classical theory. I couldn't make much progress, even in those problems. I mean, so yeah. No, sorry, I would just add one
Okay.
more thing, which is that, even if,
Mhm.
I mean, LQG, I mean, all the programs in quantum gravity, one big, I would say, big disadvantage they have is that, they take specific content, field content to be. So, for example, in LQG, you start with pure gravity. And so, let's say that you were successful and you found some very rigorous construction of Hamiltonian constraint and quantum equations of motion for gravity. But we don't know if those structure will survive if you add, say, matter. I mean, you would have to redo the whole thing. I mean, because it's extremely complicated. So, in that sense, the program has this. All the programs in pure quantum gravity have this inherent limitation that that they don't because they are not unification programs, right? So matter fields have to be added, analyzed case by case, and to me it seems like task which is I'm not sure, I mean, you find some beautiful insight. I think 3D gravity is a very good example, right? 3D gravity quantization is such a beautiful subject and people still keep finding new insights. But even there in 3 dimension, like many of the insight, if you add matter, couple matter, then they go for a toss. I mean, then they no longer, not all the insights that you see in pure gravity, obviously, and most importantly, it's no longer a topological theory, for example, if you add matter. So,
Right.
so that same type of issues you would face in any pure quantum gravity program, probably, except maybe, although I do not know much about the program, I would say asymptotic safety, because I guess there maybe they really want to do fixed point analysis of your theory, and maybe they have more nuance. Maybe it's slightly different qualitatively than programs like loop quantum gravity or canonical quantum gravity. Yeah.
Okay.
So yeah, I mean, yeah.
Okay. So the last question is that on a lighter note, what are your hobbies about except physics?
Regular hobbies, just hang out with friends, watch movies. I mean, what we do, drink coffee. Yeah, nothing special.
Okay, I see. Okay, so I think my questions are over. Thank you so much for your time.
Thanks a
It was
lot.
great to talk to you.
Thank you. Yeah. Thanks, Hassan. Bye.
So if you like this video, give it a thumbs up and consider subscribing, and the YouTube algorithm thinks that you will also like this video.